another example up here on the board. In the last couple of examples where we were using Theorem 8 to say that we could pull the limit inside if we had a continuous function, I always made a note that that was legal if we were getting a number in the domain of that continuous function. Here's a situation where that's not going to happen. Okay, so if I look, we're taking a look at the limit as x goes to 0 of e to the 1 over x squared. So that 1 over x squared that's in the exponent position is my inside part that we're plugging into the exponential function. Now, I know the exponential function is continuous on its domain. So, I have every reason to think I can just pull that limit inside and say this is going to be the limit as x goes to 0 of 1 over x squared. As long as this limit is a finite number, it's a number that's in the domain of e to the x. E to the x is continuous on its domain, and this is legal. So basically, this is okay if the limit is a number. But if I look here, 0 would make the bottom 0, but it doesn't make the top 0. I don't have an indeterminate form. So if I do my sign check, I can say, well, the top is going to 1, so that's going to be positive. The bottom is going to 0, but the bottom was x squared, which is never negative. So except at 0, it's going to be positive. So this limit would be infinity. Now, I'm about to do something that's going to make me very unhappy, because I'm going to be very unhappy if you do it. So I just want to show you this is wrong. We'll label it. I'll get my red marker to label it. E to the infinity. What's wrong with that is not only how I wrote infinity, but that doesn't make any sense. Infinity isn't a number. I can't plug it in. That is wrong. That is a mathematical atrocity, because you are treating infinity, which is a symbol or a concept but not a number, as if it's a number. But if that's wrong, this was wrong too, because that was the same thing. We violated this condition. The limit was not a number, so we aren't able to pull that limit inside. So what do we do in a situation like this? Well, what we're going to do is a substitution. I'm going to take this inside part, 1 over x squared, and I'm just going to give it a name. I'm going to call it u. Okay. So that's my problem piece, and I'm naming it u. That's just the letter u. I'm not naming it after you personally. I'm naming it after the symbol u. Okay. Now, I can certainly say that the limit as x goes to 0 of 1 over x squared is infinity. It's legal to have infinity as the result of taking a limit. Okay. What I'm going to try to do is rewrite this entire limit in terms of u's instead of x's. So we had the limit as x goes to 0 of e to the 1 over x squared. Now if I want to rewrite this in terms of u, this just becomes e to the u. As x is going to 0, we've just established that u is going to infinity. So I could write that we're taking the limit as u goes to infinity of e to the u. Now, we haven't looked yet at limits as a variable goes off to plus infinity or minus infinity. We've only seen infinity and negative infinity as the result of the limit. Our next section, 2.6, is all about limits as x goes off to plus or minus infinity. Okay. But I think we can sort of see what's the basic idea here. We're saying as u, as the input here gets big in the positive direction, what does this function do? Notice this allows me to write that I'm taking e to a power that's really, really big without committing a mathematical atrocity. I'm not literally writing infinity. I'm writing a variable here and saying that the variable is going to. infinity. It isn't equal to infinity, because that's not possible, but it's going there. Okay. Now, for evaluating this, I would simply evaluate this by my familiarity with the graph. If this is my u-axis, this would be the graph of y equals e to the u. And this is basically saying, hey, as u gets really big in the positive direction, so as we go really far to the right, what do the y values of this function do? And we can see they're going up. They're going really high up. This is just going to be infinity. So this exponential function is one where I evaluate limits as we go off to infinity by essentially just looking at the graph to see what that end behavior is. And as we start the next section, we'll formalize some techniques for evaluating limits of various types of functions as our variable does go off to plus or minus infinity. But do make a note that a substitution like this is absolutely necessary. You cannot apply this theorem if the limit that you get is not a number in the domain of the function at which the function is continuous. So you have to do a substitution like this if you're getting, when you pull the limit inside, infinity, negative infinity, does not exist, or if you got a number that was not in the domain of the function, or a number at which the outside function was not continuous.